We'll be using mostly notes today, but there is a small demonstration on MATLAB that we'll do halfway through the lecture. So I posted the script for that on Canvas. It's also a tutorial for how to implement convection codes in MATLAB too. So you'll have that as reference. But I think probably I'll just show you my screen for that, and so just focus on notes for today. Due date for homework 3. Homework 3 should be due next Monday, and so it should be due on March 1st. I think probably on the Canvas you're looking at the available date, and so there's two dates that are on Canvas. So there's one date where it's due, and then the other date which is until it's available to. And so I have it. I have the available until date set a week after the due date. So if you want to turn it in late, you can still do that. But it's due on March 1st. And so that's due
So
on Monday.
homework 2 was due March 1st.
Yes, homework 2 is due March 1st.
They were asking about homework 3.
Oh, homework 3.
Yeah.
Homework 3 is not posted yet. It should not you shouldn't be able to see it. I have it up there, but it says it's not viewable. Oh, are you talking about the PDF for homework 3? Oh, okay. Okay, yeah, and then that's a typo. I think I didn't update it on the PDF, but the homework 3 should be due the following Monday. So it should be due on March 15th. Yeah. Or March 8th. Sorry. Yeah, homework 3 is due on March 8th. Yeah. Yeah, so that's correct actually. Yeah. So homework 3 is due March 8th. So that's a week after. So, I'll post it basically after soon, and then it'll be due a week after that. Yeah. Sorry again, dates confused here. Okay, so it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing?
Good evening.
Good. Good. Oh, career fair. Is that today or is that this week? Oh, okay. I see. You guys aren't skipping the career fair for this, right? Oh, yeah. Wow, 4 hours. Jesus. Okay, it's over. Okay. I see. Yeah, it's definitely, a career fair is a lot more important than this class. So definitely, if you have to duck out for an interview or anything like that, that's way more important because it's this class is recorded, and so definitely, take care of that stuff because the class will be here, but jobs are much more important than that. Yeah. What if this class gets you a career? Maybe not directly. So I won't say that attending every day is going to get you a job. I mean, it'll help, but I think it's not as impactful as like a job interview or something like that. Okay. So today we're starting a new topic. So we're starting our unit on convection. Right. So this unit on convection, this is the last thing that we'll cover for the first midterm. So I anticipate we'll spend today and Monday talking about convection, and then we'll draw the cutoff right there. And so after the lecture on Monday, then that'll be everything that we'll cover for the first midterm. Okay. So there's a homework that's due on Monday as well, and so that homework covers diffusion. So we spent a long time on diffusion, so it's a fairly lengthy homework assignment, but definitely get working on that because that's going to be due on Monday. Because right after that homework's due, I'm going to post the next homework assignment, which is homework 3. And homework 3 is shorter. It's shorter than homework 2, but it's still a fair bit of work. So definitely, you don't want to wait until the last minute to start all that stuff. Okay. All right. And so before we get started today, are there any questions that I can answer? Okay. All right. So let's go ahead and get started. All right. So the topic for today, which we'll do today and Monday, is convection. Okay. And we're still working on finite differences. So this is convection with finite differences. Okay. Okay. And so everything up to this point, we've been working on just basically the same equation, which is just the diffusion equation. This is lecture note 06. And so this is the next set of lecture notes. And so, we've been working on just the same equation up to this point, but we've basically gone through the entire process. So we've basically taken our diffusion equation, both in 1D and 2D, and we've discretized the domain, we've discretized the equation, we've formulated the boundary conditions, and we solved it in MATLAB. So we've basically gone through the whole pipeline with all just the same equation. And so at this point, the next step is to basically, take that same process, so, the exact same finite difference process that we've been doing, and start to add complexity to it. Okay, because diffusion is kind of, it's kind of the first equation that everyone kind of works with in terms of computational physics, because it's nice in a lot of different ways, and you'll kind of see some of the reasons why it's nice as we talk about convection. And so up to this point, we've been covering this equation basically. Okay. And so at first, on the left-hand side, we have our diffusion terms. We have k times the second derivative of phi with respect to x, okay? And then we have our source term q. And then up to this point, we've just set that equal to 0, right? But starting today, we're going to be adding a term to this equation right here, okay? It's going to look like this, right? And so this new term right here this is our convection term. And it looks fairly harmless, and in some ways, it might actually look easier to deal with than our diffusion term, right? Because instead of a second order derivative, we have a first order derivative, right? And so how bad can that be? And so let me go ahead and label our the two kind of components here, right? And so first thing we have is u. And so u here is our convection velocity. And then our other thing here is d phi dx. Okay. Right. And just as mentioned, and just as what it looks like, this is a first order derivative. Right. And so, even though we've added a term to this equation here, we're going to treat it exactly the same way as we did with diffusion. Okay. And so if you remember for diffusion, the thing that we did was we took all these derivative terms and we replaced them with finite difference approximations. And what that did was it turned our differential equations into an algebraic one, which we can use to, input into MATLAB and solve, okay? But, there's going to be some complications here, because what convection adds to this equation is more than just a first order derivative. What it adds is a sense of what I call directionality. Right? Okay. And what that means basically is, how we choose our finite difference scheme is going to be, is going to make a big difference now. Okay. Because if you remember, for our second order derivative for the diffusion derivative, we only really had one choice. And so there's only one finite difference scheme that we chose for it, right? And so just as a reminder, it looked like this, not scribbles. Okay. Right. And so that was basically the only choice that we had for our finite difference scheme, right? And so I remember I did mention that there's other ways to discretize a second order derivative, but this guy works so well that there's for many cases there's really no other no reason to choose otherwise. But for a first order derivative, if you remember kind of back from a few weeks ago, we had a few different options here, right? And in particular, we had three options. And so the first option, which was the most accurate, was a central difference scheme. Okay. We also have a forward difference scheme. And we also have a backward difference scheme. Okay. And so, we have options here, right? And which one that we end up choosing and which one gives the best results, it really depends on, this concept of directionality, right? Because the thing that's unique about convection is that, remember what convection means. Convection means that convection is an active transport of a material through some moving fluid, right? And so in other words, we have a fluid that's kind of carrying our, our quantity like that, right? And so just naturally with this, there's a direction in which the fluid flows, right? And that direction is going to influence our finite difference scheme, right? And so we'll spend a good amount of time today diving into, what that means, why we need to do that, and what happens if we don't. Okay. All right. Any questions on this so far? Okay. So let's talk a little bit more about the physical meaning of convection, right? Because I think whenever you're doing any kind of computational physics, knowing about the physical intuition behind the equations really helps to inform how you're going to discretize it, how you're going to simulate it. Okay. All right. And so just like I mentioned on the previous page, convection is the active transport of a substance through a moving fluid. Okay. And so one kind of easy example that you can think of is like a fan, right? Right. So here's my fan, right? And so let's say that it's spinning, right? And it's blowing air this way. Right? Right. If you took like a bottle of air freshener or something, right? And so let's say that we have an air freshener bottle like this, and it's spraying into the fan, right? What you would expect is that the fan is going to help spread the air freshener to the other side of the room really, really quickly, right? Okay. Because the fan is kind of actively pushing it to the other side of the room, right? And so this is convection right here, right? So convection, you have a fluid, a lot of times it's either air or water that's moving to help transport, whatever that you need to transport, okay? And just naturally, just because, we have a moving fluid, there's a natural direction in which the air, the transport happens, right? Because the transport is going to happen, it's going to go from the fan to away from the fan, right? And so just some terminology that I'm going to use, for the rest of, for the rest of the lecture today. When you have a fluid that goes, in this direction, let's say left to right, when I say things are upstream, what I mean is, on the origin of kind of where the velocity field is coming from. So that's kind of in the opposite direction of the velocity field. Okay. And then there's also the downstream direction. So the downstream direction is in the same direction as the fluid. Okay. And so when I say upstream and downstream, that's basically what I mean. So think of really literally like a stream where salmon, are swimming. Right. And so, yeah. Oh, question in the chat. Yeah. So, yeah. So I mean, that's obviously that's another example which you can do for this too. So, people coughing or sneezing, anything that's particles in the air can be transported via the same mechanism. Yeah. Mm-hmm. And actually, there's a lot of computational simulations when when COVID first broke out, using these kind of mechanisms for, say, if we have convection transport of like the air that comes out when someone coughs, how far does that travel? And while the COVID still has kind of a critical mass to infect people, and so that's kind of how they came up with that 6 feet guidelines.
There was, did you see the one done in Japan where they did a fluid simulation? And they came out with like 15 feet, like the spread could be up to 15 feet.
I think I heard about that one too. Yeah. So there's definitely, and I think there's arguments about whether, what's a critical mass of like COVID particles that's enough to cause an infection. And I think I do remember seeing that study from Japan that said, you can still get it within 15 feet. But, of course, it's also a balance of, what's safe health-wise versus, what's practical too. So, end of the day, I think the safest thing is just, wear a mask, stay away from people, and, and kind of prevent those situations from happening to begin with. But, that's a conversation for another day. Okay. So that's convection, right? And so we haven't been doing that yet. So what we've been doing is diffusion, right? And so if you remember from diffusion is the passive transport. Diffusion is the passive transport of a substance, without any moving fluid, right? Right, so I think the most intuitive way to think of diffusion is to think of spreading, right? And so let's take our same bottle of air freshener. Okay. And if you spray that in a room with no airflow, what do you generally expect? You generally expect the air freshener to start to spread out from here, okay? Okay. But the spread is going to be equal in all directions, right? Because if there's no airflow, there's no reason for the air freshener particles to choose one direction over the other. So it's just going to passively spread in all directions. Okay. Right. And this is actually really convenient because if you kind of remember, how we picked our finite difference scheme for our diffusion derivative, our finite difference scheme kind of replicates this really, really well. Okay. All right. So any questions on this so far? Okay. All right. And so let's look at our finite difference scheme for diffusion, and I'll show you how it kind of mimics this passive spreading mechanism. Okay. Right. And so our finite difference approximation for the second order derivative, remember, was phi I minus 1 minus 2 phi I plus phi I plus 1, okay, all divided by delta x squared. Okay. And in particular, what I want to look at are the coefficients that are in front of each of the phi terms. Okay. Right. And so if you look at those coefficients and you look at what phi terms are involved, you can see that we need this finite difference scheme requires information from 3 locations. Okay. Okay. And so the first one, which is node I, this is the current node. Okay. 2, we have I minus 1. This is our left neighbor. And 3, we have I plus 1. This is our right neighbor. Okay. And so if I draw this on let's say like a number line, right? And so we have our 3, our 3 nodes here. And so we have node I, we have node I minus 1, we have node I plus 1. Okay. I'm going to put in the coefficients for these guys on this number line, right? And so for our node I, we have a minus 2. For I minus 1, we have a 1. And for I plus 1, we have a 1. Okay. And so I know that there's a 1 over delta x squared in there too, but this is just a a conceptual thing. So I'm just going to ignore that for now. So let's say 1, minus 2, and 1. Okay. Right. And so what you'll notice from this is that, if you kind of look at this like a scale, like a seesaw, right? So we have a minus 2 at the middle of the seesaw, and we have 1s on the ends. You'll see that this is perfectly balanced, right? As all things should be. Okay. Right. And if you compare that to, what we know physically about diffusion, right? Diffusion, remember, is a passive spreading in all directions equally, right? So it doesn't choose a direction. It just kind of goes all the way. This scheme right here kind of mimics that exactly, right? And so because diffusion is passive spreading, then our finite difference scheme should also be kind of perfectly balanced in all directions, right? And so that's exactly what's reflected here. And that's kind of exactly why, this finite difference scheme has worked so well for us up to this point, because the finite difference scheme that we choose basically perfectly mimics the physical phenomenon that we wish to simulate. Okay. I still see our participants didn't reduce by half, so we're still good, right? So no one got snapped. Okay. All right. So any questions on this so far? Does this kind of make sense about, this correlation between the finite difference scheme that we choose and the underlying physics? Okay. Okay. So that's diffusion. So that's, I bring that up not because it was broken, but actually because it works really well, right? And so now let's look at convection, right? Right. So if you remember, for convection, we have a first order derivative, and our first order derivative, we have three different ways through which we can discretize this, right? And so first, let's go over the central difference scheme. And so our central difference scheme look like this. So we have d phi dx is equal to phi I plus 1 minus phi I minus 1 all divided by 2 delta x. Okay. And so let me draw the number line again, or our little seesaw, you can think of it. Right? Okay. And if we draw the weights here, you can see we have -1 right here and +1 over here. Okay. Right. So don't worry about the sign so much. So I know we have -1 on the left and +1 on the right, but the fact is we have like a weight of 1 on both sides, right? And so this central difference scheme, just like our second order derivative, this is also a what's called a balanced scheme. Okay. And so we have, one on the left, one on the right, they balance each other out. The seesaw doesn't move. Okay. Okay. Oh, well, I'll do that later. Okay. Okay, and so let's do our forward difference scheme. All right, so our forward difference scheme look like this, right? So we had phi I plus 1 minus phi I all over delta x. Okay. So let me draw the number line again. And so we have I minus 1, I, and then I plus 1, okay? And if I draw the weights on this guy, we have a -1 over here and +1 over there, okay? Right? And so if you think of this as a seesaw, the seesaw is going to lean towards the right. And so this is kind of weighted or unbalanced with the weighting being on the right. Okay. And then finally, let's do the backward difference scheme. And so the backward difference scheme looks like this. So you have d phi dx is equal to phi I minus phi I minus 1 divided by delta x. Right. And so for the backward difference scheme, we have, this is unbalanced, but it's going to be weighted in the opposite direction. And so we're going to have -1 here and then +1 right here, right? And so this one right here is weighted to the left, okay? Okay. And so we have 3 different options for the first order derivative here, and they all have different weightings, right? Yep, so the question in the chat is, do we choose which type of convection to use, or is it given in the problem? Yeah, that's a good question. So that's what we're going to talk about, next. So how do you choose which one to use? And a lot of it's going to be based on, and I'll give you kind of a little bit of a spoilers here. So it's going to be based on which direction the fluid's going, right? And so what I'm going to do here is I'm going to give you, I'm going to draw an arrow right here, okay? And let's assume that our convection velocity is going from left to right. And so in other words, we have a positive velocity, okay? Right? And so based on the velocity, we'll be able to choose, which scheme is the best, right? All right, so question, so why is the central difference divided by 2 delta x? Yeah, it's divided by 2 delta x because we're taking kind of the difference between nodes that are 2 delta x apart, right? And so, because remember the distance between each node here is delta x, right? And so in the central difference, since we're taking the difference between phi I plus 1 minus phi I minus 1, you divide by 2 delta x. Yeah. Mm-hmm. Oh, don't worry about the spoilers. We'll get to it. Yeah. All right. So any questions on this so far? Okay. All right. And so I'll tell you what most people generally do when they come across convection problems. is that they tend to pick the scheme that's most accurate, right? And so remember when we were talking about finite differences, we had this concept of accuracy when we did all the Taylor series stuff, right? And in terms of accuracy, the central difference scheme was actually the best one, right? Because the central difference scheme was second order accurate, while the forward difference and backward scheme are only first order, right? And so kind of the first thing that people do most of the time is they pick central difference, okay? Because this is most accurate. And accuracy is good, right? If your simulation's accurate, then you did a good job and you simulated reality really well, okay? And so that's not a bad decision. And actually, you know, there's ways that you can make the central difference scheme work. But once you start adding convection into your equations, there's another factor that you have to consider that's besides accuracy, and that's stability, okay? Okay, and so we'll go over what stability is, or more rather what an unstable solution looks like kind of once we get to the, once we get later on into notes, okay? Okay. All right, and so, you know, I want you guys to kind of keep this in mind, you know, because next we're going to do an example, and I'll show you what happens when we use a, you know, an unstable solution. Okay. Okay. So let's do an example. And so let's say that we have the following equation, and then we want to discretize it using using finite differences. Okay. And so let's say that our equation looks like this. And so we'll have 3d squared phi dx squared, okay? And this is plus 8x is equal to 75 d phi dx, okay? And so now we have a, you know, for a second order differential equation where we have diffusion, but now we also have convection, okay? All right. And so before we actually go about solving this, let's go ahead and identify all the different parts of this problem, okay? All right, so first we have our diffusion term. And so, you know, even though we're talking about convection here, diffusion is still present, okay? Right. And so here is our diffusion term. Okay. And so for this diffusion term, you know, we know it's diffusion because it's a second order derivative, right? And so that's how you know it's diffusion. Okay? And the diffusion coefficient here is 3. Okay. Okay. And that's just whatever the coefficient is in front of that guy. Okay. Okay. Next, we have our source term. Right. So remember, the source term is just any function within your equation that doesn't have a derivative or no phi to it. Okay. And so there's really nothing more to add for the source term. Okay. And finally, we have our new guy here. So this is our convection term. Okay. Okay. And what I want to highlight here is that our convection velocity is the coefficient in front of d phi dx, which is 75. Okay. Okay. Right. So if you kind of refer this back to the symbols that we were working with before, our value of u here is 75. Okay. All right, and so for this problem, let's give this some boundary conditions because we can't solve it without it. Okay, and so I'm going to use fairly simple boundary conditions, and so I'm going to say that phi at 0 is going to be equal to 0, and then phi at 1 is going to be equal to 1. Okay, so we have Dirichlet boundary conditions on both sides. Okay, and so since this is a first order equation, you can solve for the exact solution. Okay. And so for this one, you have to do a little bit of math to it. So you have to use you know, the characteristic equation and undetermined coefficients. And so, you know, I'm not going to review that here because I'm not going to you know, I'm not going to test you guys on that. But if you're wondering how I got this, exact solution, that's how I got it. Right? Oh, question. Speaking of symbols, will we ever use that to solve these ODEs, or will we just straight up matrices? Yeah. So for this class, I would never ask you to solve an ODE by hand, because that's you've probably done that to death in at least 2 or 3 other classes before. And so in this class, we're just going to focus just on the MATLAB and Python stuff. Yeah. Question. So how do I know the boundary conditions? So that's given to you in the problem, and so that's the boundary conditions always have to be given to you. Okay, and so the exact solution looks like this. Okay, and so we have 589 divided by 625 multiplied by 1 over e to the 25 minus 1 times e to the 25x minus 1, okay, plus 4 over 75 x squared plus 8 over 1875 x. Okay, so it's not pretty. It's a little bit nasty, right? And so that's why I kind of decided I'll solve this one by hand, and then you guys don't have to do it. It's e raised to the 25x. Yeah, so this thing right here is an x. Mm-hmm. So this guy is an x. Oh, you mean this guy down here? This is e to the 25 minus 1. Mm-hmm. And this is a plus that I kind of screwed up here. But anyway, the exact solution is not that important. Yeah, 4 divided by 75. Mm-hmm. Yeah, so it's the exact solution itself is not that important, but I just wanted to show you that it exists, right? And so what's more important is how the solution actually looks like. Yeah. The dagger thing, oh, that's a plus sign. Yeah. Mm-hmm. For shanking the 75. Okay, and so if you actually plot this solution, it looks like this. Right, so we start at 0 right here, and then we come up a little bit, and then we kind of have a rapid increase just like that. Okay. Right, so our graph that looks like this. Okay. Okay, and so this is what our exact solution looks like. Oh, you want to go back really quick? Yeah. Mm-hmm.
Roxy, come on, this way.
Okay, great. Okay, and so this is what our exact solution looks like. And so ideally, when we discretize this with finite differences, we should get something that looks like this. Okay. All right. So now let's actually solve this with finite differences. And so let's take our original equation here, and then discretize each of the derivatives using finite difference. And in particular, we have a choice to make, right? Because we have a first order derivative. Okay. And then we can choose whichever scheme that we want for it. Yeah. Use symbols and O, D, E, I, and T. Yeah, you can do that if you want. You do have boundary conditions. It's these guys up here. Yep. Yep. So you would specify that. Mm-hmm. Okay. And so we have a choice to make on what derivatives or what scheme that we want to pick for the first order derivatives. And so, just kind of based purely off accuracy, let's pick a central difference scheme for the convection derivative. Okay. Right. And so I'm going to rewrite the equation here, but I'm going to replace the derivatives with their finite difference approximations, right? Okay. And so let's do the diffusion term first. Okay. And so for the diffusion term, we're going to have a 3 over delta x squared and this is multiplied by phi I minus 1 minus 2 phi I plus phi I plus 1, okay? So that's our diffusion derivative. And we know that this guy is great, it's beautiful. There's nothing that we need to change about it, okay? Next, we have our source term, and so we have eta xi, okay? Then we have our convection derivative, okay? Right. And so remember, I'm picking central difference here. And so central difference, we have a 1 over 2 over delta x. And then we have a phi I plus 1 minus phi I minus 1, okay? Right, so all I did there was I just took our original ODE and I replaced all the derivatives with finite differences, okay? Okay. And so from here, you know, we're gonna simplify this equation a bit, okay? Okay. And in particular, what I'm gonna do is I'm going to move all the terms with phi on the left side. Okay. And then everything without phi, I'm going to move it to the right-hand side. Okay. Right. And so in addition, what I'm going to do is I'm going to take this coefficient out in front here and then divide by it just so that our diffusion term is alone. Okay. And so we're also going to divide whole equation by 3 over delta x squared. Okay. Okay. All right, and so we do both of those things and we end up with the following expression. Okay, so we have phi I minus 1 minus 2 phi I plus phi I plus 1. Okay, and so since we divided by that entire coefficient out in front there, then our diffusion term is kind of, you know, just by itself. Okay. Next, we have a minus, and so we're going to move our convection terms over to the left-hand side. Okay, so we have a minus 25 delta x multiplied by phi I plus 1 minus phi I minus 1, okay? And this is equal to minus 8 over 3 xi delta x squared, okay? Okay, and everything on the right-hand side of that equation right there is from our source term, which I moved to the right-hand side, okay? And so we divided by 3 because that 3 came from the diffusion term, and then we have that delta x squared that also came from the diffusion term as well, okay? All right, any questions on this so far? Yeah, good question. So why did we choose central? So we chose the central scheme because it's the most accurate, okay? Because we know from before that forward difference and backward difference are only first order accurate, right? But central difference is second order accurate. And so just as kind of a first, as a first guess, because right now we don't really have anything better to go on, we're just going to pick the most accurate scheme, which is central difference. Yeah. Yes, that's a minus 8 over 3 xi delta x squared at the end. Mm-hmm. Okay. All right. And so just for the sake of, you know, implementing this in code, I'm going to simplify this a bit more, because on the left-hand side, we have, you know, several things going on. So I'm going to basically combine all the coefficients for the phi terms into one. And this helps a lot when you're implementing things in the code. Okay. Okay. And so if we combine our convection terms into our diffusion terms, we get the following. Right. So first we have phi I minus 1. And then we have the coefficient for this guy. And so we have 1 plus 25 delta x, okay, plus phi I. And we have a coefficient of minus 2 here, okay? And then we have phi I plus 1. And we have 1 minus 25 delta x, okay? And this is equal to minus 8 over 3 xi delta x squared. Okay. Right. And so the reason I do this is because remember, eventually when we write our MATLAB code for this, we're going to input a lot of these values into the left-hand side matrix. Okay. And so all of these terms here that I've put in parentheses and circled in green, these are the values that we're going to put into our left-hand side matrix. Okay. Okay. And so in addition to this finite difference equation, we also have our equations for our Dirichlet boundary conditions. Okay. Right. And so our Dirichlet boundary conditions are given by these, just simply these formulas. Okay. And so first we have, our first node here. So we have phi1. And so phi1 is going to be equal to 0 because our left-hand boundary condition was phi at 0 is equal to 0. And then our right boundary condition is going to be phi n is equal to 1. Okay. And so, these are just Dirichlet boundary conditions that you can specify in basically the exact same way that we've done before. Okay. Okay. And so, I've already implemented the script for you. And so, if you go to the Canvas site, I've posted another kind of example script for you to look at, which is the convection script. Okay, so it's kind of right below the script that we did before. And so that's for your guys' reference. And so that's just to kind of show you kind of a worked out example of solving a convection equation. But I do want to show you the result. Okay, so let me go ahead and share my screen. Okay. Right. And so if you open up that script, you should see the following. So you don't have to open it up right now. And so I just kind of want to show you the result. Okay. And in particular, I want to focus on this this number right here. Okay. Where n, remember, this is our number of grid points. Okay. And so right now I'm going to do a simulation with 7 grid points. Okay. And if we run it, you should see the following. Okay. Right. So everyone can kind of see the this graph here. So there's two lines here, and so there's a red line where the red line is the exact solution that I showed you earlier with the 4 shanking the 75. Okay. And so that's what we're trying to replicate. So ideally, what we should get from our blue curve, where our blue curve is our finite difference solution, that should be exactly the same as our exact one. But you can see that that's not happening, right? And so the blue solution is actually, quite far off from the red one, and it's doing this kind of weird wiggly thing, right? And so it starts off okay, but then as you get further and further, it starts to go down, and then it goes up and it goes down, and then you can start to see it kind of starts to become like a crazy person, right? And I'll kind of exacerbate this a little bit too. And so let's change this to actually 7, not that much. Let's do 175. Okay. Okay. And so you can see here that, as we increase the convection velocity, these, these wiggles are getting stronger, right? Okay. And so what you're seeing right here is, when your solution is doing kind of these crazy wiggles and crazy, oscillations where it goes negative, positive, this is what's known as an unstable solution. Okay. And so unstable solutions are bad, I can't think of a situation where you would want an unstable solution. Okay. And the reason it's unstable is because of our choice of the convection scheme. Okay. And so we'll talk about, what exactly made this unstable and how we can make it stable again, because we want a stable solution, not an unstable one. Okay. Implement a PID. What does PID stand for? Yeah, maybe that's one way, but
that's from our controls lab.
Oh, okay. I'm thinking of something different. So this is not really a controls problem. This is kind of a more a choice of our numerical scheme, and it has to do exactly with the fact that, remember, convection has a direction to it. Okay, and we need to pick a scheme that actually reflects that direction really well. Okay. But while I'm here, I will tell you that central difference isn't bad. Okay, so you can actually get it to work with a you can actually get central difference to work with a convection scheme. The only thing you have to do is you have to make sure that your grid is refined enough. Okay, and so instead of 7 grid points, let me choose 101 grid points. Right. And then with the 101 grid points, you can kind of see, so it's, you can't see it because they're right on top of each other, that the blue solution matches with the red one, okay? And so it is possible to get a central difference scheme to work. You just have to pick a grid that's fine enough, right? Okay. And so with 50 grid points, you can kind of see that they kind of miss each other a little bit right here, but clearly we're stable, right? So we're not doing this crazy stuff anymore. And so, we kind of have two questions that we want to answer here. So first of all, how can we determine if a central difference scheme is going to be unstable? And two, what are some alternatives to the central difference scheme that we can choose to make our situation stable again? Okay. So would it be crazy if you increase the grid points higher than 101? No, actually, that's totally fine. And so it's the only limitation is your computer hardware. And so, I have faith in my laptop. And so we'll do 1,000 grid points here. Okay. So even with 1,000 grid points, that's totally fine too. Right? So for a 1D problem, you can crank this up as much as you want. And it's the only limitation is your computer RAM. And so don't use this to crash your computer because you absolutely can. So try to keep it modest. Okay. Okay. And so let me bring back our notes here. Okay. All right. So we saw that under certain conditions, this central difference scheme can be unstable. So stability is dependent on the convection velocity. Yes, it is. Right. Okay. And so let's talk about kind of both of those points, right? So the first point that we want to make, or the first question that we had, is how can we make this stable? Okay. Oops. Okay. And so one way that we can make the solution stable that you saw was that we simply refined the mesh, right? Okay. And so what happened when we refined the grid, or what exactly was it about refining the grid that made it stable, right? And so when you refine the grid, what happened was you basically made delta X smaller, right? So the spacing in between grid points went down when we refined the grid, okay? Okay. Right, so delta X decreased. Okay. What you also saw that Joshua pointed out was that when we increased the convection velocity, that made it more unstable, right? Okay. And so how do we kind of take these two observations and then put it into one kind of simple form, right? And so luckily there is kind of a very simple thing that we can calculate, and that's known as the Peclet number. Okay. Right? And so we usually denote the Peclet number by PE. Okay. Okay. Right. And the way that we compute it is like this. Okay. And so the way we compute it is we take our convection velocity, which is U, And then we multiply it by the grid spacing delta x, okay? And then we divide it by k, okay? Right. Where k, right here, k, this is our diffusion constant, okay? Okay. Right. And so if you compute this, this Peclet number, this will tell you basically whether your solution is going to be stable or not, okay? Because in order for a solution to be stable, this Peclet number has to be less than 2. Okay. And so, you know, if you have a certain problem with a certain convection velocity and certain diffusion constant, you have to make, and you want to use central difference, you know, you have to refine your grid, you know, until, you know, delta x is small enough such that Peclet number is less than 2, okay? And so on the next page, what I'll do is I'll plug in the numbers which I had for, you know, for the previous example, and you'll see that the Peclet number was greater than 2, which led to an unstable solution. Okay. All right. Any questions on this so far? Okay. And so from that example, remember that we had a grid with 7 grid points. Okay. Okay. And with the grid of 7 of 7 points, then our grid spacing here was 1/6, okay? Because with 7 grid points, we have 6 spaces in our grid, and so that's why we have, you know, our grid spacing is 1/6. In addition to that, we had a convection velocity of 75 positive, okay? And then our diffusion coefficient, which was the number that was in front of our diffusion derivative, this was 3, okay? Okay, and so with all this in mind, let's compute the Peclet number. Okay, so the Peclet number is U, which is 75, times delta x, and so delta x is 1/6, divided by 3, okay? Which is our diffusion number, right? And then what you get from this is a Peclet number of 4.1667. Okay. Right. And so obviously here, you know, because the Peclet number is greater than 2, this led to our unstable solution, right? Okay. And you saw that, you know, with the grid spacing of 7, then we had an unstable solution, right? It's 75. Mm-hmm. Right. And so if you're dead set on using a central difference scheme, which is not a bad choice, you know, I've been kind of you know, disrespecting central difference scheme, but it's not a bad choice because, you know, no matter what, central difference is going to be more accurate than forward or backward difference. Right? And so if you want to use a central difference scheme, the only thing you have to make sure is that you refine your grid enough until the Peclet number is less than 2. Okay. And so you can actually compute, you know, what's the grid spacing that you actually need, right? Because we know that Peclet number has to equal to 2, okay? And then from this, we can compute the grid spacing that we need, right? Okay. Okay, so all I'm doing is I'm just, you know, using that same formula, but making delta x an unknown, right? And so we can see that delta x is equal to 3 times 2 divided by 75. Okay. And so this is 0.08. Okay. And so if your number of grid points in your domain is such that, you know, your grid spacing is 0.08, then, you know, you'll have a stable solution. Okay. And if you equate this out into, you know, if you actually do that for our domain here, which has a length of 1, that means if you set n is equal to, well, you can't do 12.5, so let's do 13. Okay. And so if you set your n is equal to 13, what you'll see is you know, what you'll see is that your solution will be stable. Yeah. Our question is K always given? Yes. Yep. So the diffusion constant, that's always going to be given to you in the equation, and the equation will always be given to you, for these problems. Okay. All right. So that answered that question. Okay. All right. Question: Peclet equal 2. That's 75. And so all I'm doing was plugging in U and K from the previous problem. So U was 75. Okay, so that answers the first question. So the first question was, remember, how do we actually get the the central difference scheme to be stable? And here's the answer to that. And so if you want to make central difference stable, you just have to compute the Peclet number. Okay. But what if we wanted what if we want to make our solution stable no matter what? Okay. And if we want to make our solution stable no matter what, then we have to choose a different differencing scheme. Okay. Okay. And so to motivate that, let's bring back our number lines here. Okay. So we have I minus 1, I, and I plus 1. Okay. Okay. And then let me draw our convection velocity here. Okay. Okay. All right. And so if you remember from our central difference scheme, we had something look like this, right? And so we had a balance scheme where we had a weight of -1 on I minus 1, and then a weight of +1 on the on I plus 1. Okay. Okay. All right. And so there's a better way that we can do this. Okay. And in particular, what I'm going to tell you is that the problem is actually this guy. Okay. Right. Because with the convection velocity, things are naturally flowing, or you can think of, information is flowing in the same direction as the velocity, right? And so information is traveling from upstream to downstream, right? Where the upstream direction here is on the left, and then the downstream direction here is on the right, okay? And so what we're doing here is that, what we're requesting here with the finite difference is that in order to compute this derivative, we need to get information from upstream, which is this guy. Okay. Okay. And so that's upstream of the velocity field, but we also need information downstream. Okay. Right. And so the downstream direction doesn't really make sense because you can almost think of it as like the velocity hasn't even gotten there yet, right? And so the velocity is going from left to right. And so if we want to get information about, this convection derivative, it doesn't really make sense to kind of pull information from a location that, the flow hasn't even gotten to yet, right? Because the flow is going from left to right, okay? And so what we should choose, or in other words, the difference scheme that we should choose is something that's weighted on the upstream side, okay? Okay. Because, because if you try to get information from downstream, it's almost like if you can imagine, you're spraying air freshener into a fan, right? And so if you're at the very tip of the kind of the air freshener, right? And you try to get information about the air freshener ahead of where the air freshener is going, that's not really useful information because the air freshener hasn't even gotten there yet, right? It makes more sense to get information about the air freshener from, your current location and somewhere that is visited already, okay? And so, when you introduce convection into your equations, you have this kind of natural, natural sense of direction, the direction in which information travels, which is to go from upstream to downstream, okay? And so when you're choosing your finite difference scheme to model this, you should pick a finite difference scheme that places more weight on the upstream side versus the downstream, okay? Okay, any questions on this so far? Okay. And so for this particular example, since we have a positive velocity going from left to right, let's pick a backward differencing scheme, which places more weight on the upstream side, okay? Okay. And so the backward difference looks something like this. Okay. So we have I minus 1, I plus 1, okay? And so backward difference has a minus 1 here and a plus 1 here, okay? And so you can see it's kind of lopsided onto the left-hand side, right? Which makes a lot of sense because we have our convection velocity that's going from left to right, okay? And so just like we kind of mentioned, we want to kind of lopside this so that we have more weight, or it's more kind of lopsided on that upstream side, because that's where the information is coming from, or that's where the flow is coming from, okay? Okay. Okay. And so if you redo that previous example such that you use a backward difference scheme with a, instead of a central difference, what you'll see is that even with, n is equal to 7, then you're going to get a stable solution, okay? Okay. Okay. And so it doesn't matter how many grid points or what your grid spacing is, your backward difference scheme will always be stable, okay? And sometimes that's what you want. And sometimes you just want to make sure that, no matter what you do with the grid and no matter what you choose for the velocity, you're going to get, you just want a stable solution, okay? Okay. And so, I don't have the script prepared, but I can at least show you, what the solutions would look like, okay? And so are there any questions on this so far? Okay. And so here's what the graphs would kind of look like. Right? All right, so the question is, so was it a lie about central difference being more accurate? It wasn't a lie, and so central difference actually is more accurate. And so actually, there's an interesting decision that you always have to make when convection is present. And so you can either pick central difference and go for accuracy, just knowing that you have the risk of being unstable if your grid isn't fine enough, or you can pick backward difference and then make sure that you get a stable solution, but with the caveat that your solution is going to be a little bit more inaccurate. Okay, so here's what the graphs would look like. Okay, so let's look at n is equal to 11 first, or n is equal to 7, sorry. Okay, and so remember, this was the case that was previously unstable for the central difference. Okay. Okay, and so here is the solution, the exact one, and then our finite difference one would look something like this. Okay. And so you can see it's not that close. So it's not that accurate, but at least it's stable. Okay. Right. Yes, exactly. So sometimes you have to make a choice between stability and accuracy. Right. Okay. All right. Question. So does that mean we'll have situations where we can't refine the grid? Yeah, that's a great question. So there will be situations like that. Probably you wouldn't see that in a 1D case because you kind of saw when I was doing the MATLAB that I could basically crank it up to thousands, 10,000s. Like I think even my computer can even handle up to 1,000,000 grid points, and you can refine in order to make basically anything stable with central difference. But that's 1D. But in 2D and in 3D, what you'll see is that the cost of refining, is a lot greater than it is in 1D, and it kind of scales up exponentially. And so, in 3D, which is kind of where a lot of people work with engineering simulations, refining the grid sometimes just isn't an option, just because you don't have enough computing power, you don't have enough memory, and you don't have enough time. Yeah. Mm-hmm. Right. So question. So then is more stable and less accurate solutions will then be told how far, oh, hang on. So yeah. So, it's hard to say, what a specific threshold is for, for accuracy and stability, because a lot of times that depends on, what you're ultimately wanting to get from your simulations. But I'm for this part of the class, I'm just letting you know that there's kind of this trade-off in between. And kind of more realistically, what you need to know is that when you're working with codes, like commercial codes out there, you should learn about what kind of schemes that they use for particular things, right? Because that choice of scheme is going to affect things like stability and accuracy. And so when you're debugging your simulations and trying to get them to match with an experiment, which dials to press and what doing what will affect what. Yeah. Mm-hmm. All right, and so let's look at the solution with n is equal to 100, or I guess 101. Okay, and so if you remember for the central difference, when I cranked up the number of nodes to 101, then this basically put the graphs basically on top of each other because central difference is really accurate, right? Okay, but because backward difference is not as accurate, what you can get sometimes is something like this. Okay, and so obviously you get a solution that's stable and it looks good, but it's like it's not quite there. So, it's kind of, still off by a little bit. Okay. And this is the result of the fact that backward difference is only first order accurate, right? And so you're just not going to get as accurate a solution, but it's stable. Okay. And so that's kind of a trade-off that you kind of have to worry about sometimes. Okay. And so, I'm presenting this as kind of a trade-off, but, for this class, you won't really see that trade-off except for our 2D problems. Because for 1D, no matter what central scheme you use or what the velocity is, you can probably kill it with enough nodes such that you'll get a stable solution. Okay, but for like we mentioned, for 2D and 3D problems, it is a real decision that you have to make because refining your grid sometimes if you have a sophisticated 3D model, if you refine your grid, that might be the difference of your simulation finishing in 3 hours versus 3 days. Okay. And that's a real thing. And so I know a lot of CFD, computational fluid dynamic simulations that run on supercomputers for like weeks at a time, right? And everyone hates them because they hog up the whole machine with their turbulence and say, oh, look how cool my turbulence is. And you're like, yeah, you hogged up the whole machine for like 3 weeks. I hope you got some good information from that because no one else could do anything else while you're doing that. And so it's a real, it's a real concern, especially, because computing really comes at a premium a lot of the times, especially for those, for those big, heavy simulations. Right? It's not as simple as that, because a lot of times, these simulations are run on supercomputers where, you're running on, hundreds or thousands of processors in parallel. Yeah, gravitational waves is one of those things that really eats up computing resources. And so, what they choose for their grid and how they choose to trade off stability and accuracy is a real trade-off for them. And they have to make some really tough decisions on how they do stuff. Yeah. Okay. Let's see. Yeah, if you overclock too much on a supercomputer, you might cause a blackout or something. All right. So before we head off for today, I do want to leave you with one parting thought. Okay. And so, what we saw for this example problem was that, for a convection velocity that goes from left to right, right? And so in other words, the convection velocity is positive, right? And so it goes in the positive x direction. The differencing scheme that we chose for this was backward difference. Okay. Right. And the reason for that was because it weighted our differencing on the upstream side, right? And so we had more weight over here versus over here, right? And so we get more information from the upstream side more than the downstream. Okay. Okay. And so, that's when convection velocity is positive. Okay. And so, I want you guys to think about what happens when your convection velocity is negative. Okay. Okay. And so when your convection velocity is negative, that means it's going from right to left. Okay. Okay. And so, in a 1D case, right, where you have, you can choose either forward difference, backward difference, or central difference, what scheme would you choose here to make sure that this guy is stable? Okay. And remember, stability, at least in terms of convection, is you want to put more weight on the upstream side. Okay. But when your convection velocity is going in the opposite direction, then the upstream side is opposite from what it was before. And so in order to make this stable, we have to do this, right? Or not that actually. So I think it's -1 and 1, okay? Right, and so in order to make this stable, we have to choose a forward difference scheme for this. Right? Yep. Mm-hmm. Right. Because the forward difference scheme in this situation will place more weight on the upstream side more than the downstream. Okay. Okay. So any final questions on any of this before we wrap up for the week?
I have a question.
Sure. Mm-hmm.
Is there any way that we can use information from the exact solution to try to predict or like refine the difference formula?
Yeah. No, that's a great question.
A bunch of methods for like forward, backward difference, and like in other books.
Yep. Yeah, no, it's a good question, and a lot of times, maybe not the exact solution, but a lot of times, experiments, like you run an experiment on a certain phenomenon, or you collect some data, those are used to inform the solutions as well. And so, in terms of exact things that people do, it varies depending on the type of data that you have. And so, in this particular case, for our exact solution, not necessarily in terms of the differencing scheme, because we kind of explained everything in terms of that. But what we can see from this solution here is that on the right side of the solution, we can see that we have a rapid increase, right? And so at first, our solution doesn't really seem to be doing much. But then once we get to the right side, then we really start to ramp up like that. And so what people tend to do is that in areas where you have kind of rapid change, okay, or in other words, you can say that the slope here is really high. Okay. Then what you can do is you can selectively refine your grid only in those areas. Okay. Okay. Because like we talked about before, when you refine your grid, you usually increase your cost by a lot. But usually what tends to happen is that there's only one specific area or one specific region in your simulation which is causing the issues. And so if you know what that area is, either based on some data or based on your knowledge of the exact solution, you can selectively just refine the grid in that area. And so what happens there is that you get an accurate solution there, but then you don't kill yourself with the cost. And so that's kind of one way that you can use knowledge of the exact solution or data in order to better inform how you simulate it.
Mhm. Okay, so it's 6:45, so that's all we got time for today. So thank you guys for tuning in. And so remember, the homework is due on Monday, so that's homework 2. And then homework 3, I guess you guys can see the PDF for that already. And so if you're already done with homework 2, definitely get started with homework 3, because the lead up time for that is a lot shorter than before. Okay. Okay, and so as always, reach out if you have any questions, and have a good rest of your evening. Have a good weekend, and I'll see you guys on Monday.
Thank you, Professor.
Thanks, guys. Thanks, you too. Right. Daniel, Sean, did you guys have any more questions? Okay, so if not, I'm gonna go ahead and close the call. So then I'll see you guys next week.